You can also imagine this, maybe you've been riding on a carousel or merry-go-round. If you stand right at the middle of that merry-go-round, you're not going to feel a lot of motion. But if you stand farther out towards the edge, you're going to feel like you're moving really fast just because you have a greater distance between yourself and the center of rotation. And so this whole idea is kind of expressed by this one equation, v equals r omega. This symbol here is called omega. It's a Greek letter, and it's commonly used to denote angular velocity. And so simply put, this is just saying that if you multiply the distance from the center of rotation to whatever point on the rigid object, and you multiply that by the angular velocity, you'll get the linear velocity at that point. I see someone's raising his hand, so feel free to ask your question, unmute.
Do they have the same RPM?
Pardon?
Shouldn't they have the same RPM?
Yeah, so in terms of angular velocity, this pen has, if I'm spinning it around, it has a constant angular velocity. So with respect to the center of rotation, every point on this object has this exact same omega, the exact same angular velocity. And if that's the case, how do they have a different linear velocity? How is this point at the tip moving faster than this point that's close to my finger? And the answer to that is that they have a different value of this constant r here, or this number r, which is the distance between the center of rotation and the point of interest. And so you can think about being on that carousel again, on that merry-go-round. No matter where you're standing on it, you're still going to make the same number of revolutions per minute as anyone else, because you're not moving relative to the merry-go-round. Regardless of whether you sit towards the edge or towards the center, after 10 seconds, you're both going to make one revolution. And despite this fact, you're still going to be moving faster in terms of linear velocity because you're at the edge, so your value for r is greater. So even if omega is constant for 2 points, it depends on r, what your linear velocity v is going to be. And so that's kind of a conceptually maybe novel concept, but if you'll remember last week, I had spent some time talking about how rotation is not an intuitive concept and people get it wrong all the time. Just think about what the equations are, think about what the math says, and it'll lead you hopefully to the right answer. And so one direct application of this principle, this connection between the angular and the linear worlds, is that we can start thinking about wheels in a different way. In an ideal world, in a perfect situation, wheels would not slip. So at every point, a wheel, I don't know if you can see, I'm holding like a metal disc in my hands. If you have a wheel, it will always roll perfectly. And it'll never do this. It'll never slip along the hand, but for it to move horizontally, it always has to roll to meet my hand, right? And that's this perfect world that we're imagining where wheels never slip. In reality, of course, wheels slip all the time. We talked about how in steering, you can't avoid slipping of the wheels just based on the geometry. So in the real life, you'll always have slipping of the wheels, but for now, we can pretend, we can imagine for our calculations that wheels don't slip. And given this fact, it actually opens up a very useful connection to what we just talked about with the merry-go-round, where you can determine how fast the robot moves simply based on how fast the wheels are turning. There's going to be a direct relationship between the velocity of the robot itself and the angular velocity of the wheels, or the acceleration of the robot forward and the angular acceleration of the wheels. And so this is where we start to get into some of the usefulness of these ideas. So for this one, you might want to maybe draw a picture, but consider the case where you're looking at your robot and the wheels are turning at 200 RPM. Maybe you know this because of the programming or you're measuring it, but the robots are turning at 200 RPM without slipping. You also know that the wheels have a diameter of 3 inches. And so from that, how fast is the robot moving in feet per second? I'll give you another few minutes to think about this problem. Hopefully, just seeing this problem helps you realize what kind of important things that you can do with this kind of concepts.
Understand the encode. But you have the encode what you want was the this one.
I guess for those of you who forgot, the circumference of a circle is 2 pi r. Or pi times d is perhaps. And you're free to leave your answers in terms of pi if you want. I see someone asked about that. Or you can just write the decimal approximation. The apostrophe, the double quote, this is inches. So in general, the one of these is feet and the 2 of them is inches. So I'm seeing a few different answers. I guess I'll give it another minute or two. This one is a bit involved in the units, I suppose. In fact, every answer that has been presented so far has been a different answer. So this one, maybe we'll go through this one together. Oops. All right, I'm not seeing new answers, so I'll start by asking you, how far does the robot move with 1 revolution of the wheel? So you have this no slip situation, this ideal world where the robots are always against the ground. Given that that's the case, how much distance do you get when you let the wheels revolve once? And you may want to refer to this handy formula here for circumference. Make sure to include your units if you're sending chat messages to me. So you can imagine that you have wheels that are not slipping. When the wheels make 1 full revolution, the distance that traverses is the circumference of that wheel. So we can simply say that if the wheels revolve or turn fully once, then it travels the circumference. And hopefully that's fairly intuitive. So 1 revolution is then 3 pi inches. And another way you can express that in terms of feet is 1/4 or 0.25 pi feet. And that's just a simple divide by 12 to get feet. All right, and now we take another fact. It's moving, the wheels are turning at 200 RPM. So you know that in 1 minute, it makes 200 revolutions. And so in 1 minute, how much distance does the robot travel? Given that fact that with 1 revolution, it moves 3 pi inches or 1/4 pi feet. How many of those does it do in 1 minute, given this fact? I see a lot of unitless answers or units that are not the ones that would be appropriate. But yeah, I see one of the answers is 157. That can also be expressed as, say, 50 pi feet per second, or rather per minute. And that's the last thing you have to do, just convert that per minute to per second. So how do you convert from something per minute to something per second? And I'm starting to see some answers. So yeah, I've seen several answers to this effect, and they're saying something like 2.6. And so yeah, I would agree with that. That is the conclusion that I arrived at. So good on you if you did that, I suppose. I'd say 2.6 feet per second. And yeah, there you go. So hopefully that was something useful. You probably know the diameters of the wheels of all your robots. If you don't, you can measure them. And if you make this no slip assumption, which is a big assumption, but in terms of calculations that you're presenting, maybe it's probably good enough. You can determine how fast you have to turn these wheels in order to travel a certain speed for your robot, right? So sorry if I'm asking you to unmute, by the way, in the Zoom. It's not intentional, but when I move stuff around, I sometimes click on these buttons. So I'm not asking anyone to unmute, but I may be clicking on that accidentally. All right, so that's that. One last thing before we have a short break, I'll introduce to you is angular and linear acceleration. So we just did angular and linear velocity. Now we're going into acceleration. And this is where it becomes a lot more complicated because, as I've stressed many times, velocity is a vector quantity. And when you have vector quantities, you kind of have to do math with the vectors differently. And all of this is to say that it's not quite as simple for acceleration as it is for velocity. Turns out when you have things that are turning around other things and they're also moving around, acceleration becomes really, really complicated. It has all these different terms. And it's not easy. So the simplest way that we can address this is to just consider the tangential acceleration. So you may have learned something about centrifugal forces before in school, in physics, in physical sciences. And whenever you have a rotating object, you're going to have a force, some influence that causes things to move towards the center of rotation. You can imagine this, like if you're sitting in a car and the car turns suddenly, you're going to kind of feel like you're being dragged towards like the outside of the car, right? And that's kind of this centrifugal force effect. In order to be constrained to a circular path of motion, you need to be experiencing an acceleration inward. So all that is to say that acceleration is not quite as simple, but we can still do the same treatment that we did with angular velocity by just considering the tangential component. And what that tangential means is, you probably know about tangents. Maybe if you were in like the Onshape classes, you know the tangent constraint. For math, you probably know what tangents are, but it's a line that touches a curve at only one point, right? It's like, it's the opposite to the normal vector, so to speak, where it just perfectly matches the curve at that point. So that's kind of what the tangential acceleration refers to, where it's the same direction as the velocity in this diagram, where the tangential acceleration is kind of in the direction of these arrows if the angular acceleration is in the direction of this arrow. And so again, the concept of angular acceleration is that you have something that's spinning and it's spinning faster over time, or it spins slower over time. And if you have that effect, you're going to have some kind of linear acceleration at every point on this rigid object. So what we can do essentially is we can kind of start looking at acceleration in the rotational way of thinking of things. And that will be related to motor selection, right? Since motors have ratings for things like power and rotational velocity and their torque, and we'll talk about what that means later on. When you're picking a motor, you're kind of thinking about things in the rotational realm, but your ultimate goal may be in kind of this linear world where you're worried about how fast the robot can move in a straight line. You're worried about maybe creating some kind of linear or reciprocating action. And so kind of the relevance of these concepts of angular acceleration, angular velocity is kind of to make a relationship between picking a motor and picking other components that allow your robot to do some kind of useful work. So this question might be a bit, I suppose, a bit vague without a diagram, but suppose that you have a robot that's accelerating at 1 foot per second. Maybe it's rolling down a hill, so its speed is getting faster. And you know that the wheels of the robot are 6 inches in diameter. And then we also apply our no slip condition, where in the perfect world where the wheels don't slip, then you can determine what is the angular acceleration of the wheels. And since we're considering the tangential acceleration, the reasoning, the logic here will be similar to that which we applied for this scenario with the angular velocity. So again, I'll give you a few minutes and then we'll take a break. Someone's asking about angular acceleration. So the idea is pretty analogous to acceleration for distance. This is like acceleration for an angle. And so it's the rate of change of your angular velocity. So if you have something that's spinning, it's eventually going to slow down and stop spinning because of friction. And so that's kind of an angular acceleration where the speed of the spinning is slowing down. The main idea is that if you're trying to have a rigorous treatment of acceleration due to rotation, it's going to be really complicated because of vectors. But if you only consider a very specific part, it's fairly straightforward. And this problem is kind of analogous to the speed example, where you can determine the angular acceleration just based on the condition that there's no slip the diameter of the wheels, and the acceleration of the robot. So actually here, it's 7:25. So like I said last week, I know that long classes can be kind of tiring. So I'll give you like a 5-minute break and we'll reconvene at 7:30. We can go over this problem and we'll talk about other things. So enjoy your quick break, and I'll see you again shortly. All right, welcome back. I guess one thing which I realized I did not say, which may have been helpful perhaps, is in terms of the tangential acceleration, we have this kind of relationship which is analogous to the relationship here, v equals r omega. Similarly, we have a for tangential acceleration is equal to r times alpha, where alpha is the angular acceleration. And so with this kind of relationship, we can determine just with these quantities that we have what the angular acceleration is. You may have gone about it differently, thinking about the circumference of the circle, and that leads to the same result, but knowing this fact may have been helpful. In any case, the answer, I did get a few, but I guess what I would say is be conscious of what units you're using, make sure the units seem correct. In this case, for example, like the angular acceleration here can be found by dividing the tangential acceleration, which we know, by the radius. And so we have 1 foot divided by, say, a radius of 1/4 of a foot. And that comes out to an angular acceleration of 4 radians per second. So you can convert that to degrees per second, or I guess some of you like RPM per second. But yeah. That's that for now. We'll put aside kinematics for the moment, and we can start talking a bit about dynamics. So up to this point, we've just been talking about kind of how things move based on a set of rules. It's a very pure description of how things move, but we're also going to be interested in what causes the motion. So what makes the robot speed up, what makes it slow down, what makes it stop, and we can attribute this to a number of factors. Maybe the motor is making it speed up. Maybe, I don't know, air resistance is making it slow down as the robot gets faster. Maybe it's stopping due to the brakes on the robot. I guess maybe you don't run brakes since it's an electric motor. But that's kind of what we're going to get into. And one of the very important concepts in terms of dynamics is something called force. And you've almost certainly heard the word force before, but maybe you don't have a clear idea of what exactly is a force. And to be honest, I'm not sure if it's easy to provide a very clear understanding of what is a force, but one very common definition that's used is some kind of push or pull that can cause motion. You may have heard of Newton's 3 laws of motion. Those are all kind of treating this thing called force. So what you really need to know about force is that it's a vector quantity, which means you have to indicate a direction of the force. So are you pushing it up, down? And in a kind of qualitative sense, you want to know what kind of force you're dealing with, whether it's a contact force or a force that acts at a distance. For example, if you rub your hands together, it's not necessarily, easy to rub your hands together because of the friction involved. There is a force that stops your hands from just freely sliding against each other. I guess more applicably, if you push a block on a table, it's not going to move forever because there is a force, the friction, that acts on that block. The other force that probably is the one you see most commonly day to day is one that we call like a normal force. It's essentially the answer to why things don't fall through your table, right? If I'm holding up this pen in my hand, the pen can't just fall through my hand because there's a force that's keeping it up, right? You'll observe here in the simple experiment, if I let go of my pen, it drops to the ground, and that's because it's being acted on by a force called gravity. And so the fact that it's not just moving down, it's not falling straight to the ground, there must be some force that's imparted by my hand onto this pen to keep it from falling. So that's kind of the idea of normal force. The reason it's called normal force is because it acts in the direction normal to the contact surface. Normal meaning perpendicular. So if you have a sloped ramp, the normal force will be pointing in this normal direction, kind of up into the side. And so you'll see that something will roll down a ramp because its normal force is not straight up, it has a horizontal component. The other kind of force we deal with commonly are things like gravity and magnetism. So hopefully you're all familiar with gravity. It's the force that makes things fall down towards the center of the earth. If you drop an object, it's going to naturally move towards the center of the earth, which is the ground for most cases. There's also magnetism, which you're probably familiar with. I have a couple of magnets right now in my hand, which I'm trying to take apart. All right, so I have these magnets here. They're pretty strong, and you'll see that when I move them close together, there's a force that makes them want to be attracted to each other, even opposing gravity. So there's your quick summary of what gravity is. And what I'm going to introduce now is kind of one of the most important equations in terms of classical physics. And this is something that you'll see referred to as maybe Newton's second law of motion. You've probably seen this before, called like F equals ma. And this is just describing what effect force has on the motion of an object, or what you can deduce about the forces that are acting on an object based on how it's moving. So the statement is here, it's pretty simple. This is another Greek letter, it's a capital sigma, and it refers to a sum. So if you add up all of the forces that are acting on an object, that is equal to the mass times the acceleration of that object. I guess the simple example, I'm holding up an object on my hand here, and it is currently at rest. It's not moving, it has no acceleration. And so that means that the sum of all forces that are acting on it, both the gravity pulling the magnet down and my hand that's pushing the magnet up, those must sum to 0 such that the total acceleration of that magnet can be 0. We'll go more into detail on this next week when we talk a bit about statics, but you're definitely going to see this again. I'll just introduce it for the time being so that I can introduce this other concept called torque. I know today's been a lot of new vocabulary, new concepts, but I'll probably go over this again next week just so you have this repeated exposure to the ideas. And I hope you'll believe me when I say that they're very important ideas when it comes to understanding how to design something in terms of mechanical engineering. And so this concept of torque is kind of the rotation way of thinking about a force, right? They're different things, but a force is to linear motion as a torque is to rotational motion. And so I said that a force is some kind of push or pull. A torque you can kind of think of it as a twist that tends to produce a rotation in an object. It's also referred to as a moment. If you hear someone talk about like a moment in terms of classical mechanics or dynamics, they're probably talking about a torque. And again, it's a vector quantity. You can tell the direction based on that right-hand rule. And the way that you go about calculating a torque is this equation here, which is R cross F. And if you don't know about vectors, don't worry about what that means exactly. All you need to know is that the torque is determined by the product of the moment arm and the force. So in this case, you can try thinking about a door, right? When you're opening a door, the moment arm is kind of the distance between the place where you grab the door and the hinges of the door. And so if you've ever tried to open a door by pushing right up against the hinges, you'll find that it takes a lot of force. It's really hard to open a door by pressing up against where the hinges are, as opposed to if you were to push against where like the door handle is. And that's because this quantity R is different in both cases. If you have a small R, if you're pushing right against the hinges, you're going to need a really big F, a really big force to produce that same rotation that opens the door. So just keep that in your mind. If you have any questions about that, just ask, but I'll just leave it at that kind of conceptual definition level. And we'll come back to it later when we talk about like statics or motors. So with that, I'll kind of change course into machine component, which is gears. And I'm sure you've seen gears before. You probably use them in the transmission for your robot or in some of the components that are like actuated or that rotate. Even if you don't explicitly use gears, you probably use something like a servo motor, which has a gearbox inside of it. So gears are pretty important. And like to put it simply, like it's a machine component. It's essentially a wheel that has teeth on it, and it meshes with other wheels with teeth on them to make them rotate together. So there are a lot of different effects that gears have. The first one that you might notice is that if you have two gears, the rotation of the second gear will be in the opposite sense as the rotation of the first gear. So I have some demonstration gears here. I don't know if you can see my camera. Maybe I need to stop screen sharing. We have two gears here. And when you have two gears that mesh, you'll see that when you rotate one, the other one has to rotate in the opposite direction. They can't both rotate clockwise. They can't both rotate negative or counterclockwise. But they have to go in opposite directions. So one use of gears is to change the direction of your rotation. Another use of gears is to change the location of your rotation. So maybe I use two gears that have the exact same number of teeth. They're the exact same gear. And the only thing I want is to change where the rotation is happening. So I'm effectively moving this kind of axis of rotation to another place. And that might be useful. Maybe your motor can't fit in the robot right where the wheel is at because there's not enough space, but you can kind of move the motor over and put a couple gears there just to put a bit of space between the motor and where the wheel is. So that's another use of gears. And I guess perhaps one of the most important uses of gears is to reduce or increase the torque that's going through your system. So your motor is going to produce a certain amount of torque at peak loading. At different conditions, it's going to have some amount of torque that it produces. And the purpose of gears is to kind of change the torque that's going to your wheels. Transmission is everything that sits between your motor, your source of power, and the wheels. And the gears are probably going to be part of that. You might want to increase the ratio, decrease the ratio. But the ultimate aim is to amplify or reduce effectively the force that you're going to be putting on the ground. When it comes to gears, we have a lot of different types. The most classic one, the one that I just showed you, is a spur gear. And these are the most simple kind of gear. The teeth just are cut straight. They look kind of like spurs on riding boots, I guess. Maybe that's why they're called that. And that is in contrast to helical gears, which you'll see they kind of have teeth that spiral. They look a bit like you might imagine the mechanism wheels do, where the teeth of the gear kind of curve along. They have an angle when you look at them face on. And so there's some advantages, disadvantages to that. You can imagine they produce different forces within the gearbox itself. Helical gears are quieter, which is why they're usually used in automotive applications. Some other types of gears, maybe you haven't seen as much. There's a worm gear, which is kind of bottom left picture is showing, where it looks kind of like a screw, and the threads of the screw are what's turning the teeth of the gear. So it's pretty interesting when the axes of rotation are not parallel to each other. And you also have bevel gears, which allow you to transmit rotation at different angles. And that's kind of this bottom right image. And if you're curious about gears, there's really a lot of literature out there regarding gears, since they're so important to industry and machines and automobiles. But that's a quick at a glance look. And now we get to how you should pick gears when you're designing something. And if you ever look up nomenclature for gears, if you look up like vocabulary or the different parts of a gear, there's going to be a ton of words describing all the different geometrical parameters of what makes a gear a gear. And in most cases, you don't need a lot of those geometrical parameters, things like, I don't know, the diameter of the base circle. The point is that there is going to be a lot of numbers associated with gears that don't matter too much, but there are a few numbers that are very important. And these numbers here are some that you'll probably need to think about when you're picking a gear for whatever thing you're designing. The first one, perhaps the most obvious one, is how many teeth the gear has. So if you can see my camera, this gear here has 15 teeth. And the importance of the number of teeth is that it kind of determines the ratio that you'll get from your gear. The next quantity is called pitch diameter. So this is what you can think of as the effective diameter of the gear. Essentially, you'll see that a gear is mostly circular, but there's not one circle that you can use to describe the diameter of this gear. You could pick like this smallest circle that can fit around the gear. You could pick the biggest circle that you have that fits completely inside of the gear. There's all kind of diameters, but the pitch diameter is the diameter you should use when you're determining how far apart you should place your gears. So let's say that you're tasked with designing a gearbox and you need to know how far apart the holes should be. In that case, you should use the radius, the pitch radius, so to speak, half of the pitch diameter. You should add those things up, and that's the distance that the axles should be for your gears to mesh properly. So number of teeth, pitch diameter. The next one is something called diametral pitch, and the next one is pressure angle. And these two refer to some kind of geometric property of the teeth. The exact details of how these are calculated, you probably don't need to know. But in order for gears to mesh properly, if you're buying gears or printing gears, you need to make sure that they have the same diametral pitch and the same pressure angle. And depending on if you're using metric or standard gears, it might be called something like module. So module or diametral pitch, or maybe just pitch, and pressure angle. Those need to be the same for the gears to work together. If you go and find like CAD models on McMaster and you pick gears with a different diametral pitch or a different pressure angle, they're not going to mesh. And the last parameter which you're probably interested in is the face width, which is how thick the gear is. So if you just look at the gear face on, that thickness is the face width, and it can have an effect on like how strong your gear is. The higher the face width, the stronger the gear, just because it's thicker. So I'll leave it at that. When you're picking gears, make sure you know what these numbers are going to be, because it will determine whether or not your gears will work properly together and some of the geometric properties of your gears. So this picture kind of illustrates the importance of knowing the pitch, where both of these gears have 30 teeth. But if you just told me that you picked a 30-tooth gear, I could get two very different things, right? You could give me the gear on the left, which is much smaller than the gear on the right. And if all I told you was to pick a gear with 30 teeth, you could pick either of these without knowing which one that I actually wanted. And the next thing that we're going to go to is what's called the gear ratio. So when you have more than one gear working together and the gears have different sizes, when you have a gear that you're driving, there's one that's going to be connected to the motor, that's called your driving gear. And the one that's connected to it, the one that's probably at your wheels, at the output, that's going to be what's called your driven gear. And in most cases, these gears are not going to be the same ratio. So they're going to spin at different speeds. If I take a smaller gear, I'm going to have to turn it more times in order to turn the bigger gear one time. So kind of the way we express gear ratio is kind of this ratio here, the number of rotations you need to turn your driving gears in order to produce a rotation of your driven gear. Another way you can calculate this is using the number of teeth on the gear. So if you're, you'll notice that it's kind of the other way around for this ratio. If your driven gear has more teeth, you're going to need to turn your driving gear a greater number of times in order to turn that driven gear once. So I'll give you a couple examples here. The number of teeth on the gears are shown here, and I just want you to briefly think about what the gear ratios will be for these two cases, where in both cases, the gear on the left is the one that is driving, and the one on the right is the one that's being driven. So gear ratio, you can express it as like a number and a colon and a number, or just as a decimal. But take a moment to think about that. So I don't see any responses, but as I said in like the slide before, you can express the gear ratio just as kind of this ratio between.
Hold on, when you're supposed to respond. Nobody responded, you know, everyone responded. François, on.
If you guys not respond, I will check the chat.
All right, I'm getting responses. So
Okay.
yeah, people are speaking. So yeah, most people seem to say, in the case on the left, 1 to 2, in the case on the right, 5 to 6. And so as you can see, it's pretty straightforward. You just take the numbers of teeth and you can derive the ratio that way. Another way you can go about it is using the pitch diameters, where the way that it was defined is kind of the circles that you would want to be in contact for the gears to mesh properly. And so you can imagine that they're going to trace out the same, they're going to have the same contact point. So you can use the ratio of the pitch diameters, if you know that, also to get this gear ratio. But that's a pretty simple example. We also have cases where you're designing gearboxes where, for whatever reason, you need more gears. In this case on the right, we have 3 gears in sequence. This gear in the middle here, that one is called the idler gear. On the right, let's say that we have our driving gear, or on the left, we have our driving gear. On the right, we have our driven gear. And you can imagine the motor would go here on the left and the wheel might be out here on the right. And so in a case like this, you can kind of do the same math where you take the gear ratio between the driving gear and the idler, and then the idler and the driven gear. What's interesting is that you can also take the ratio between the driving gear and the driven gear, and the idler gears. What you'll find if you try doing the math is that they'll cancel out. So you can take a moment to think about that. One of the advantages of having this kind of system is that in this particular case, the driven gear and the driving gear will have the same direction of rotation, and the idler gear will have the opposite direction of rotation. So for example, if you want your motor to drive forward, and for that to cause your wheels to drive forward, then you'd probably need an idler gear in the middle there to achieve the desired rotation direction, while still having the reduction you want. The other thing to note is that having this idler gear places the gears farther apart. So if you need to achieve this greater distance between your motor and your wheels, you could just stick in a couple idle gears in there, and at the cost of some efficiency, you'll get that greater distance. So in this case, the ratio for this system, you have 25 teeth in your driven and 30 teeth in your driving. So you can just take the ratio like that. You turn this big gear 5/6 of a time to turn this gear once. The other case where you have multiple gears, you might have a system like this compound gear train, where one of the gears is attached to another gear. So they're not meshed with each other, but they'll rotate together at exactly the same rate. So in this image here, you can see, let's say that we're driving this really big gear, the one with 30 teeth, and attached to that gear, we have another gear that has 15 teeth. And meshing with that gear, we have our driven gear, which has 20 teeth. And so in this case, I guess in this case, it's very simple just because effectively the driving gear is the same as the compound gear. So in this case, it's not really that interesting, but you can imagine if I had 4 or 5 gears, I could attach another gear in compound with the 20-tooth gear, and then that could create a different ratio that I might not have been able to get with just the gears in sequence. So that's another strategy that you can use. And one more thing in terms of gears, we have a system called a rack and pinion. So the pinion refers to essentially a smaller gear. And what this allows you to do is convert a rotational motion to a linear motion. Last week, when I talked about how cars steer, we have something called a steering rack. And inside of that, we have this rack and pinion system where you're turning the pinion, you use your steering wheel to spin the pinion in an rotational way, and that'll cause a linear motion in the rack where it'll move left and right depending on how I turn that pinion. And lastly, in terms of gears, a common type of problem that you're going to see is where you have some kind of requirement for how far apart your axes of rotation are going to be. Maybe your axle, your output shaft, and your input shaft from the motor. And you need to achieve a certain kind of ratio. So the real challenge becomes that you have a catalog of gears, maybe some gear vendor, different set of gears that you're allowed to use. And you need to be able to span a very specific distance using a set of gears and also to achieve a desired ratio. So it becomes a very interesting, very complex problem, especially since you have like 2, even 3 dimensions to work with. But if you're trying to get an idea of what kind of problems that you would be solving with this kind of information, maybe when you're designing your robot, you know that the motor has to be placed or mounted at a certain point on the robot, and you know that the axles are going to be somewhere else, and you know the distance between these 2 points. Well, then you have kind of a gear design problem where you need to span a certain distance, you need a certain ratio, and it's up to you to make a gearbox, right? So that's that. In terms of things that are not gears, of course, gears are not the only way that you can transmit rotation from one axis to another. The other most common ones are probably the chain and sprocket and the belt and pulley, where if you have a bike, your bike is driven by a chain and sprocket. For a belt and pulley system, if your car has what's called a CVT, a continuously variable transmission, that's an example of a belt and pulley system. I guess one that you're probably familiar with is like a conveyor belt, or I think it's called a conveyor belt at like the supermarket or the grocery store, where you're checking out and they have like a belt and a pulley to move your items to the counter. So these are common transmissions and they have their advantages and disadvantages. What you'll find is that implementing something like a chain and sprocket is probably more expensive, but it also has some advantages of being more efficient, and it's possible to fix a chain and sprocket, as you might have experience with if you've fixed a bike before. The other point is that a chain and sprocket is probably going to be pretty loud because you have the chain and the sprocket, you have metal pieces banging against each other. In terms of a belt and pulley, you might use this transmission as well. The advantage is that it's cheaper at the cost of perhaps not being repairable, since you have to replace the belt entirely when it stretches, and it's a bit less efficient since the belt can slip against the pulleys. So things to keep in mind as you're designing a transmission for your robots. You can imagine that the ratios are calculated in similar ways, just based on the geometry, based on the diameters of the belts, or rather the diameters of the pulleys and like the sprockets, right? So we'll move on from transmissions now, and we'll talk a bit about motors. And a motor is essentially a device that can produce some kind of rotation. And here we have an example of a DC motor. So it works on electricity, specifically a direct current. We also have like a combustion engines, which is kind of an example of a motor. But the goal here is to use some kind of stored energy to produce a rotation. And that's probably what's driving all of the moving parts on your robots, where you have some electrical energy stored in a battery, and you're trying to turn that into rotation at the wheels or at whatever is being actuated. And so in terms of specifically this DC motor, I have this kind of demonstration here to explain how they work. The idea is that if you have a magnetic field, so if I have my magnet here, any current, any electricity that's flowing through a magnetic field will experience a force. And as we talked about before, a force is something that like pushes or pulls. And what's useful about that is that if I have my wire, let's say this is my coil of wire here. If my wire is live, it has current flowing through it, then I can produce a force on this coil of wire just by having a magnetic field there. So you can see on the left here, in this example, I have a single wire with the current going through it, and it's in a magnetic field. And that means that it'll experience a force, in this case, like upward. And so how can we turn this into rotation? The first thing that you're going to try, you're going to have this kind of coil of wire, this loop of wire, where on the left side of this loop, you have current going in the upward direction. In this rightmost coil, you have current going in the downward direction. So you have two lengths of wire attached to the same rigid object, and they have current flowing in opposite directions. And what that means is that they'll experience forces in the opposite direction. So I have my coil of wire here in my camera, and I have a magnetic field that's being applied from the side. So I have like a magnetic field going outway, like sideways across my screen. And in this case, if there's a current going through the wire, it's going to experience a force that tends to turn it so that it's facing now up and down like this, so that the parts of the wire where there's current flowing perpendicular to the magnetic field, it reaches a kind of equilibrium. And you can see that in these middle diagrams. And so that's half of what we need. Just given a live wire loop and a magnetic field, we can get any loop to kind of align in a specific direction due to the forces involved. And all we need to do is find some way to make it keep doing that, make it go a bit farther, then align the other way, then go a bit farther, then align the next way. And one way that we do that in terms of DC motors is we have something called like a split ring commutator. And it's a big word. All it means is that it allows you to switch the direction of current in the wire. And what you can imagine is that when you do that, suddenly the forces that are keeping an equilibrium are now facing the other way. So it goes from like a stable to an unstable equilibrium. And since it already has a bit of that angular momentum, it's already spinning a bit, it's going to tend to keep spinning. The direction of the current is going to change, it's going to reverse, and suddenly the forces are making it want to align this way again. And so it just keeps doing that, and it'll spin as long as you have that source of direct current, right? And I have this video on the previous slide that shows this model of how a DC motor works. I prepared this because I might not get the live demonstration to work, but yeah, it might not work on the video, but you see that the principle is sound and that DC motors do work in real life. So if you needed convincing on that, here you go. Most of the motors that you use probably are some form of DC motor if they're powered by battery. There also exist AC motors, which can work on something like wall power, which is alternating current. Those are a bit more complicated in how they work. And you probably aren't using like a combustion engine on your robots. Just at the scale, it probably isn't the best tool for the job. So what you're using is probably some form of DC motor, whether that's a servo or a stepper motor or something like that. And so now we can kind of get into connecting this back to this concept of torque that we introduced earlier in the second half of the class. Just to refresh you once more, a torque is some kind of twist, some kind of influence that tends to produce a rotation in an object. So what we saw kind of before, we have a bunch of forces that are involved in this whole DC motor setup that cause a rotation in this coil of wire. And the coil of wire is going to be connected to some kind of output shaft for your motor. And so now we kind of treat that motor as like a black box. We don't really care about how the motor works anymore. All we know is that it produces what we call a torque. And so if you connect something to a motor, it's going to spin because it's connected to that output shaft. So let's consider a very simple case of how we might use a motor. Let's say that we have a system set up where we have an arm, we have a motor attached to the base of the arm, and the job of the motor is to give the arm the ability to support a load, a weight at the end. You can see kind of in this diagram, it looks maybe like a catapult. And we're going to use the most simple case where conveniently the force is perpendicular to the moment arm. So the moment arm is horizontal, the force goes down due to gravity, its weight goes down, and the motor is at the other end. And so, as you might recall, rigorously speaking, the torque is a cross product, but since that's a bit advanced mathematically, we can just think about this perpendicular case. In order for the motor to be able to lift this load, it needs to be able to produce a torque that is going to produce a force that can balance the weight of the load, right? And so in this bottom diagram here, I kind of labeled the quantities of interest. The first one is this M for moment. It's the torque that's produced by the motor. Then we have F, which is the force. This is the load that's produced by whatever's at the other end of your arm. And finally, we have R, which is the distance between where the motor is operating and where the load is. And so with these quantities, we kind of establish this relationship, which helps you determine whether or not your motor is strong enough to do the task that you're interested in, the task you have at hand. And so this will lead me to my second, I guess the second project for the class. Last week, you were designing, I guess, like something to pick up an object. I guess this is an extension of that where you're picking up an object, but now you're trying to design the arm to make sure that you're actually going to be able to lift the object. So the prompt here is to design an arm that can be mounted on a robot, on a motor, which can pick up a ball with a certain weight on it. And don't worry too much about the mechanism of how you're going to articulate or manipulate this ball. Just assume that it has it already scooped up, like a spoon. And all you care about is that the motor is strong enough to support the weight of that ball. So what I'll give you, and these slides are on the Google Classroom, so you can look at this for yourself. We'll say that the motor produces a constant torque of 1 Newton meter. The units here just arise from the fact that torque you can get by multiplying a distance and a force. So a meter is a distance, a force is a Newton. I guess Newton times a meter. And you also have this ball that weighs 10 Newtons. And if you're not familiar with Newtons, you can kind of think about it the way that we colloquially treat a kilogram as a unit of weight. Like if I say that I weigh like 70 kilograms, I weigh 80 kilograms. If we're speaking rigorously, that's not really a true statement. It would be that I mass 70 kilograms or I mass 80 kilograms or whatever. But if you make the approximation that the influence of gravity has like an acceleration of, let's say, 10 meters per second, then a Newton is just an expression of how many kilograms you might colloquially say that you weigh. So if I say that I weigh like 70 kilograms, then I would actually weigh like 700 Newtons. It's not correct to say that you weigh a certain number of kilograms, but it is correct to say that you weigh a certain number of Newtons. So that's the way you can think about it. A 10 Newton weighing ball is probably around a kilogram in mass. You can ignore the weight of your arm, but the constraint is that you have to have an arm that's at least 20 centimeters long, so 0.2 meters. And your task here is to determine the appropriate length of the arm. And if you think that you need a gearing ratio, you need to determine what gearing ratio you're going to use. And what I want you to do is just show some calculations and draw a schematic of where your motor is going to be, what gears you're going to have, just draw like circles for the gears, and show your arm and the length of the arm. And I just want you to draw like a simple diagram. It can just be boxes and circles, but have those, mark all the distances, show your calculations, and show that it'll allow the motor to support a weight of this ball at whatever distance that you decide. So you can make it longer than 0.2 meters. You can imagine there's some advantages and disadvantages of having longer arms. Yeah, so in terms of what you want to submit, I see a question in the chat about it. Just draw a diagram kind of like you did for the previous assignment. It can just be like circles and rectangles, and just label all of the numbers that you think are relevant. So the length of the arm is probably important. The number of teeth on the gears, the diameters of the gears might be important. I'd say if you have any doubts, just present what you think would be a reasonable explanation to get your idea across. Like, if I needed to make this thing, tell me about the gears. How many teeth should the gears have? How big should the gears be? How long should this arm be? And that's pretty much all that there really needs to be described. You can make of this project what you want, really, a challenge by choice, so to speak. But I just want you to think about what you would need for a system to meet this kind of constraint, given what you know about this extremely idealized perfect motor that produces a constant torque at all loads. And assuming that the arm is always in this horizontal position, since the math becomes a bit more complicated if it's not. And I guess in the last few minutes, I'll just share an example. This equation is really what's key here. So you can imagine that, let's say that I have a 5-foot beam. I guess I'll use metric because it's easier. I have a big 5-meter beam, and it's going to be driven by some kind of motor. Let's say that at the other end of the beam, I'm supporting 100 Newton of a load. So what torque would I need to apply to the other end of the beam in order to keep this system statically stable in a horizontal position, right? In a position that looks like what you see in this diagram. In that case, I would need to apply a torque that is 5 meters times 100 newtons is equal to 500 Newton meters. And that's the value of this quantity M that I need to apply to the other end in order to ensure that I can have this stable horizontal beam with the force applied at the end of 100 newtons. And the reason why I say that the weight of the arm is negligible, in reality, the weight of the arm itself is also going to add a load to the motor, but you don't really need to think about that for this. I just want you to get an idea of how to work with this quantity called torque, and to get some more practice drawing things, conveying your ideas, since that's really what's important here, to be able to have an idea and to explain to someone just with an illustration that kind of speaks for itself. And so final words for the next week, just submit to Google Classroom by Saturday. And I'll see you again at the next Sunday class, where we'll probably be talking about, I guess, statics and designing things to be strong, I believe. I guess one more thing, next week I'd like to use a bit of Onshape, which is like a browser-based CAD program. So I know a lot of you probably have experience with Onshape, and based on like some of the classroom submissions, I think some of you did use Onshape for that. So if you don't know what Onshape is, look it up, try to make an account, but I will go over it briefly next class, so don't worry too much about that. But yeah, other than that, yeah, have a good week.